My name is Mikhail Khludnev. I work for a company Dynamics. Our customers are American retailers. We develop high-load backends for them. And we also have project in big data field, in cloud, and so on. But I work in the most interesting department, in search, definitely. Okay, we will start from introduction discussion to briefly touch key aspects of query customization. Then we look into essential Lucene data structures and searching routines, some key search classes in Lucene. And then we look on the core algorithms of executing complex queries from classic information retrieval. And then we come back to custom queries and fully covers this topic. Check a few examples and potential problems on query customization with performance and so on. And in the end, I'll show you one more example of custom query, which will not about search, but about like gathering additional information from search results, and it's just an example how you can bring additional value for your business with custom queries. So let's start introduction discussion. We will not talk about custom query particularly, but we will discuss standard functionality that might be cheating, but it's okay for now. How you can search across few fields in Solr. So if you have a few words entered in search box, how you can search these fields, these words across few fields? How to do that with Solr? It's obvious thing. How you can search in Solr across few fields? With this max query handler, right? Like query parser, right? And this query parser generates query something like this. This is the correct form of the query which is created by this max query parser. Is the correct one? Do you think so? No, it's incorrect. So this max query parser generates something like this. And here is the first point of query customization. So why that handler generates particularly this form of query? Because of particular business requirements. And for this query parser, we have the following requirement that if we search one word across two fields, like this, right, we count on the maximum score from hits to these fields, right? And then we need to sum scores from per word disjunction, from per word maximum. This is the business requirements for particular query handler, and there's a key point that you might have different requirements, right? And when you implement some custom query, right, you focus on particular business requirements. Here's the first point. Also, here you can see the two approaches of query customization, of using custom query solution. The first solution is like generate like combination of standard queries, like this parser does. And the second approach is create your own query classes with necessary scoring or matching logic, like it was done for particularly this query parser, and for it the junction max query was implemented, especially for it, right, for support grid requirement. And its scoring logic differs from standard Boolean query with optional clauses. Okay, that's all for the game. Let's look into Lucene. So that's should be obvious thing. So you all know about university index. You attended yesterday's session from by Michael Lush. Right? It's just my example from Wikipedia, and that's how we call both parts of university index. And here is the layout of this data in Lucene index. So you can see how Lucene actually works, right? When you specify some term, it finds this term in the term dictionary, reads the offset, then go by this offset and read posting list. It's worth to mention that above these two files and internally in it, there are many other like additional data structures and comprehensive algorithms to make search more efficient. And how old is university index from your point of view? How old it is? What do you think?
40 years.
What? 40?
40 years.
Here's implementation from 15th century, so it's already worked at that time. Okay, and we're going to discuss query execution, right? And query execution in Lucene is done by using scores, right? And we will tell about scores so much. We need to figure out what is scorer. Scorer is a simple abstraction, is just iterated by posting list, right? It's forward-only iterator, and here's the API of Lucene Scorer. So you can see that essentially Scorer is an iterator, right? You can check where it's positioned right now. You can move it to the next document, or you can advance it to the given document number, right? Right, and because Scorer is a scorer, right? It should comply with its name. It introduces the method of getting the current score, getting the score for current document. And here's how all Lucene queries are built. There are a few abstract classes, right, where the abstract query create abstract weight, and abstract weight create abstract scorer, and every concrete Lucene query extends these classes and provides all implementation. Like this one, it's the essential query from the Lucene. It's term query. Term query is like color equal red, something like this. And this loop shows how to actually use Scorer to find all documents and score them. Right? You just loop them by next doc and check the score for the current document. Here's the core Lucene search classes. We have public facade, which we call searcher. It has public method, which accepts query and collector. It searches for the query, reads index file from separate abstraction, which is called index reader, and put result into collector. Where a collector is a fairly obvious thing, but sometimes it's worth to comment what it actually does. Here's the example of what collector does. We search for some query, and this query finds 2 and 7,000 results, right? But collector picks the first page of result with the best score. So that's what collector does. It just picks up the first result with best score. That's all. Let's zoom the previous diagram, and we see like how searcher collaborates with query to create scorer, and then it delegates searching to the scorer. And it's a great approach because searcher actually searches nothing, right? It fully delegates to scorer, and it allows to have different search implementation driven by particular scorer class. And then scorer collaborates with collector for putting search result into it. Here's the last and the most detailed diagram. You can use it as reference material. It just right now it's worth to comment about this huge loop frame. As you know that you cannot update inverted index, right? It's almost impossible. Because of this, when you amend some documents in the index and commit them, the separate standalone segment is built and added to the segments chain, right? And every time Lucene search for document by enumerating this chain of standalone segments of inverted index. So, and what this loop is about, and you can also see that scorer is created for searching on single segments, searching for segment on single segment only. And then the small loop frame is just collaborated, is looping through found documents and putting them into collector. Should be clear. Let's look into how the complex queries are executed, because for a while we looked only on term queries, trivial ones. So the first algorithm is documented time search. In this algorithm, we enumerate documents to merge posting list and calculate score for every document. That's how it works in Lucene. The first step, we create scorers and position them onto the first document in posting list. And then on every step, we arrange scorers by the current document ID. it looks like this. And it allows us to pick up scorers with the least document number. It looks something like this. And we can put document with number 0 into collector with score 2. And in this talk, we use simplified scoring function. We just count the number of scorers which are positioned on the same document number. It just gives number of matched query terms for the document. And then we move scorers to the next document, something like this, and arrange them by current document again and pick up scorers which are positioned onto the document with the least number, something like this. And the last step, we put the document with number 2 with score 3 into collector. The opposite approach is term time search.
Some of those words stop words. Do you really calculate score on A?
Okay, so in this example we also index and query for stop words. So it's a sort of artificial example. It's not like how you need to build your search system. So it's not guide about practical usage of Lucene and Solr. It's just example, just simplest example from Wikipedia. So don't consider it as a guide for building search systems. Opposite approach is to process posting list one by one, and because we process posting list one by one, we cannot calculate final value of score for every document. Because of this, we need to accumulate partial scores in the accumulator and update them while we process posting list one by one. And only after we process all posting lists, we've got final scores for document in the accumulator, and it allows us to move or to push all these results from accumulator to collector. Looks like this. Okay, now we know 2 core algorithms, and now we need to choose the best one. Reasonable? Okay. To do this, we need to solve the simple algorithm problem. The problem is estimating the complexity of collector work. Right? So how complex is collecting first page of search result? Let's we have a query which finds n results, n search results, and score them. And collector need to pick up the first page with the best scores. Scores is the second number. So what is the algorithmic complexity of this, of finding this first page, and what's the algorithm of doing this? You should know this. It's what? Yep. It's implemented with priority queue, and priority queue is used to be built on binary heap. Sure. And it works something like this. We arrange the first, we arrange our results in binary heap, right? And they put every from n document found into this heap and adjust the heap, right? As a result, we have this first page of search result, and it's clear that the algorithmic complexity of collecting first page of search result is n logarithm k, right? We've heard it's yesterday's session, something like this. We also need to introduce these variables. The Q is the length of the query, just number of terms in this query, and P is the summary length of all posting lists from query terms. Right, and now you can tell me what is the algorithmic complexity of searching by the second algorithm by the term time. What is the complexity? Can you tell me? This algorithm consists of 2 stages. On the first stage, we process all postings, right? and then we run collector. And reasonably, the complexity is just the sum of complexities of these 2 stages, right? At the first stage, we process all postings, and then we run collector. No, nothing special here. And what about the first algorithm, about documented time? What do you think? Whether it's better or worse than the term time? What do you think? Sorry, what? Worse? Yeah, well, to answer this question, we need to remember that we have to arrange scores by the current document ID after processing every posting, right? We could actually sort them on the every step, but it's not really efficient, and because of this, the same binary heap is used also there, right? We store the references to the scores in the binary heap adjusted by current document number, and we just move scores and readjust the heap. That's how it works, but it adds logarithm Q into the complexity estimation, sadly. Let's estimate the memory consumption. What you can tell about documented time search, so how much memory it consumes for docket time search. One heap. And which heap? But what about this heap? Don't you need to keep it also in memory? Right. So as a result, we have quite modest memory consumption. Right? We just need to keep 2 heaps in memory, and it's quite convenient. You see that they should not be so huge. Right? This algorithm can be run in parallel, simultaneously, and it means that it's highly scalable algorithm. Right? It's really convenient for practical usage. And what about memory consumption for term time? Is it worse or better? Yep. We need to accumulate a lot of. We need to accumulate all results in the accumulator, right? And at the time when Lucene was created, it was not even possible, right? Because JVM heaps was really small at that time, right? And now it's possible, right? We can do this, but if we can do this, we cannot run this search in parallel, right? Simultaneously, right? This algorithm doesn't scale. And you might think that Lucene does not provide implementation for term time search because it has worse. It's too expensive to be there. But in fact, term time search was the first algorithm which was established in Lucene in according to the names of the classes. And this algorithm explained in this white paper written by Doug Cutting, who is known as author of Lucene and Hadoop. And beside of this algorithm of term time search with limited memory consumption, he also explained all this complexity estimation and detail of this algorithm, which we've looked at right now. So it's really worth to read. It's really valuable knowledge. And here's the algorithm of Boolean scorer, which is term time search implemented in Lucene. So how it works, how you could solve it yourself. So what's your idea for solving this problem with huge memory consumption? How you can implement that accumulator? What's your idea? How you can create this accumulator for accumulate partial scores? What you will use? Which data structure?
So if you don't know how many documents you got, it's fast to manipulate it, right?
So you think about the worst case, right? But okay, even if you have plenty of memory, what you will use? I think that hash data structure is reasonable thing for implementing accumulator. Sorted, but no, we don't need to sort the partial score because we update them, right? And we need to. Yep. And collector can do this by limited priority queue. So it proposed to use hash, something like this, and limit this size of this hash by some particular length. Just in Lucene, it's 2 kilos of elements, and at this slide, it's just 2 elements. And the problem number 1 with hashes is collisions, right? And we need somehow to resolve collisions, and it's really painful thing with hashes, right? And the approach for managing collision here in Boolean Scorer is just avoid collision by separating whole search onto stages. And on every stage, it processes only chunks from the posting list, and the length of the chunk is equal to length of the accumulator hash. And because of this, there's no conflicts. So you can see how it works. And the first step, we process only first chunk from every posting list and put the elements into hash without collisions, right? And after we finish with the first chunk, right, we can put these documents into collector because we never meet the same documents again, right? And after that, we can start with processing the remaining chunks, something like this. So tournament time is done by chunks. Nothing special. And there is a minor question, how to enumerate elements which was placed into this hash table during the search phase. So how you can enumerate all elements in this hash? What's your idea about it? So the first approach is just linearly scan it, right? But what if you meet only few documents during the one search phrase? Right? You will waste a lot of steps, right? A lot of efforts of just scanning this hash, right? And because of this, the element which is placed into hash table are linked all together, one by one. And as a result, we have a linked open hash table in Boolean Scorer 2. And it actually yields one subtle problem about searching performance. Because right now, when we follow these links and enumerate all elements, we enumerate them out of order, which is not like it works with docket time search. Because in docket time search, documents which are put into collector are always increasing, with increasing document number. And here, because of linking, they are somehow reordered, right? And I actually wanted to observe this problem and discuss it in detail, but I found it really complex and subtle. Right? Just all what I can say is that collector has this special flag and special logic, and there are even special collectors which handles these cases, collecting results out of order. And I'm not sure it's optimal and reasonable approach in Lucene right now. So, but it's question to committer and to committers, and it's worth to discuss further. It's just a snippet which shows how Lucene chooses one algorithm from another. So you see that collector should support out-of-order scoring, and there should no mandatory clauses, like it works only for disjunction queries. And you also can see the scorer classes which are used for both algorithms. This and this. And they also interesting details that Solr never chooses Boolean Scorer, so it never works with tournament time search. So due to some reasons, it loses some possible performance gain, but it's question to committers also. Just to wrap up and summarize this section, if we have short disjunction query, which algorithm you prefer to choose to search for short disjunction query? What's the feeling? The query is short and it's with optional clauses. Which algorithm do you choose? There is no significant difference between two algorithms, right? So there is no matter which algorithm actually to choose. It's a question for particular measurement, for benchmarking, right? But we cannot choose proper algorithm from the theoretical consideration, right? Because the length of query is small and we have no significant gain from the estimation complexity. But if the query is really long, which algorithm you'll use to execute this query? Tournament time. Tournament time because it should faster than documented time. Because with documented time, you need to arrange all these scorers by current document ID after processing every score. Scorer. And at practice, the difference between this algorithm can reach like few times, right? On practical problems, you can get few time gain between these algorithms, and that's what we're losing with Solr due to some reason. I don't know, but it might be corner cases, not so important for vast majority, might be. Okay, and the next reasonable question is which site visitor can enter such huge query? What do you think? So who will enter such long query? In which site you can meet such long query?
If it's just some kind of e-commerce site where you select filters, maybe?
But filters is handled separately by filter query in Solr. So actually no one can enter such long query, but many search systems, for example, like our system, has really aggressive query preprocessing logic. And in fact, queries might be even more like bigger and deeply structured, and it might be really more complex than this. So it's a valuable question for practice. That's my point. And what if we have query with mandatory clauses? What if we have conjunction? Which algorithm we will use to execute conjunction query? Term time or documented time? Which one is more reasonable?
Documented time.
Documented time, because there is no sense in scan all posting lists if we need just intersect them. Right, and conjunction query execution is really important for the practice, and we will look into it in a little bit more, a little bit deeper. So it works something like this. We create scores and position them on the first document in posting list. But now we need to move scores to the document number 2, because it's clear that document with number 0 doesn't match the query, right? It's clear from this, right? And we start to move all scores to the document number 2. It works for this posting list, but this posting list has no document number 2, and in according to the contract of advance, it lands at document number 3, right? Now it's clear that document number 2 is absent in result, so it doesn't match the query, right? And we need to move all scores to the document number 3. And after all scores are positioned into this document with the same number, we can calculate the score and put this document into collector. Something like this. And you see, like, scores like jump one above another or push one each other, and committers often refer to this way of executing query as a leapfrog. So you see leapfrog in mailing list, so it's about the executing conjunction query. And leapfrog is highly desirable way to execute query because it's faster rather than enumerate all documents by next doc. And for sake of complexity, I have to derive this estimation. It is not accurate, it's like optimistic estimate, but you can see that at least you need to n time position Q scores on the same document number, right? And we do not actually derive it more accurately because despite this formula looks like the previous ones from disjunction queries, conjunction queries runs way faster, and you know why. Actually, right? Why can conjunction query runs faster rather than disjunction query, despite of the formula looks pretty the same? Do you have an idea?
Number of document matches so much.
Right, because primary complexity factor is the length of the search result, and regularly, of course we can create few corner cases where it is not right, but almost usually, right? Result from the same conjunction query is much shorter than the same result from disjunction query, from the disjunction same terms. And we can just declare or state that conjunction query is way faster, they produce a much shorter result, and they use leapfrog for executing. And I'm not sure what of these statements are cause and what are consequences. It's just reality, it's just experience. So we end up with algorithmic section. We've seen how we can execute disjunction queries and conjunction. And the last slide, which I decided to add to this section, as a key design consideration for Lucene algorithms, and it's our reasonable expectation about Lucene performance. You see that Lucene searches by the complexity is just linear to the length of search result. It's quite different to the relational databases, which sometimes can fall to the full count, to sequential count. And in that case, the searching complexity is linear to the size of initial, so the number of all documents, right? It's not proportional to the valuable results. And here's the Lucene advantage. And also, Lucene tries to limit memory consumption, which makes it quite handy for practical usage, and it's suitable and scales really well. Something like this. That's what we can expect from Lucene. So let's come back to our core subject, to query customization. We'll look into one example of custom query just for this section. And then we observed the strategies of generating custom queries. And then we look at two Lucene features, which is worth to mention too. And then we observe a few performance problems, which you can meet on the way of customizing queries. Here's the example of custom query. For this example, we index terms without tokenization. So, for example, it's from e-commerce space. So, for example, if we have multi-word brands like Calvin Klein jeans, we index it as is with keyword tokenizer. So, without separating term by text field type. Okay, and now if visitor search for 3 words, we can match the 3 words as separate terms. So we consider it as a valid match. And we also can match them as a single term with 3 words in it. So these double quotes is not phrase query, it's just Java string notation. Okay? And we also can match the 3 words to the document which has like B word term and single word term. So it's just an example of custom query which we will use for this section, right? And you can see it searches for full coverage without interchanges, without overlap. And this query did not accept regular text matches like this one. Okay, is it clear what this query is about? What it does? Like, I need to understand the problem. This query searches for coverage. Okay, it's okay. It's just example. Okay, how we can do that? Right, the first thing which we recommend to do that is extend Boolean query and Boolean Scorer 2, because Boolean Scorer 2 provides documented time search which is easy for extension. Right, that's what we recommend to do. And here's a crucial thing, that this scorer inherits the collection of children's scorers. And children's scorers is scorers which are produced by subordinate query clauses. That's what we need to implement open match verification or open scoring logic in that scorer. In fact, this plain collection of children's scorers will look something like this. So you will see all this while you will debug this query. So you can use it as a reference. So the documented time scores always looks like DAG of such scores, which applies necessary logic, necessary matching logic, something like this. That's how you can implement NextDoc for this score, right? Look what you need to do. You need to start the loop. In this loop, you need to delegate to the inherited NextDoc implementation. And that inherited code will move and advance children's scorers. And then you can run match verification method, which will watch the position of children's scores and apply open match verification logic and run the loop if it doesn't comply with requirements. Here's idea of advanced implementation. It's something like this, but if match verification fails, it delegates to the same nextDoc method, right? Which will run the loop for the documents. And here is a sample match verification method for these particular requirements. Look, we need to loop children's scores and check where they are positioned right now. And if this children's score is positioned on the same document where the parent score is positioned right now, we can count the query which produced this children's score as match for these documents, right? And then we can compare the summary length of text from the queries, subordinate query clauses which matches these documents. So that's how we can implement that particular query. Okay, it should already work. Here's two strategies of generating custom queries. So the first approach is just combine standard queries into a huge and deeply branched query tree. It looks something like this. You can see that this complex query matches to these three words as separate terms, and it also matches to the triple word term, right? So it complies with our requirements. And the one thing you need to keep in mind is that when you combine alternative matches in such queries, you need to use disjunction max query rather than standard Boolean query with optional clauses. So it's like this max query parser to dust. It's worse to do. One of the advantages of this approach for query generation is that you can flip standard query operators to drastically amend the matching or scoring logic. For example, if we flip from conjunction to disjunction, we relax matching condition, but we have the same condition for scoring, for evaluate score. So we will match as regular text match query, but we will score for coverage. That might be handy for you. And we also don't need to forget that in Lucene we have fields, and we always search for particular fields. Because of this, we need to multiply all this huge tree to the list of fields. As a result, we have something like this. So that's where that scary queries comes from this. And this is really, works well technique. And I almost like it, but I have few concerns about performance because in this query tree we duplicate same nodes, right? And I suppose it might somehow impact the performance. Because of this, there is an alternative approach is to generate flat disjunction query, which is just Cartesian product, which enumerates all desired texts and all necessary fields. Right, and then you can apply match verification logic by the method like we saw before with verify match, right? So and that method you can apply necessary procedures for scoring or for matching. And the last thing about query generation is that you need some sort of framework, right, to model these query nodes and trees, like. And we recommend to use flexible query parser, which is already exists in Lucene. So it's just good point for starting, for building your own query generator. It's standard one. We also met the problem with steadiness, but it's a little bit subtle and legacy. So we saw it only in Lucene 3, so I decided to cut it off, so it's not actual, it doesn't happen in Lucene 4. So there's a quite high chance that you will not miss, you will never face this problem, this score steadiness. But we can come back to it if you wish. Okay, and then now before observing performance problems, we need to look at the two standard functionalities in Lucene. The first is mean should match. How many of you familiar with mean should match? Okay, so so at least I need to understand why I need to explain why mean should match is important for practical applications. For example, for e-commerce. If we have few words entered in our search box, right, we cannot run this query as conjunction. And do you have an idea why? Why we can run just conjunction queries from entered words? What if you run the three words as a conjunction query? Or even empty result? Because it's highly probable that user makes typo, and the most evil case that it refers, it's not here, but it's happened quite often when people refer to the different product categories. Like they refer to quite different products, and because of this, the intersection of these terms is 0, right? And the empty search result is really sad case for e-commerce site. Right, and we try to avoid it. And if we run these three words as a disjunction query, we have the opposite side of this problem. If these words refer to different product categories, we have a huge list of results with a high divergence in it. And classic information retrieval says us that it's not a problem, it's even great, because we always can apply magical relevancy function, right, and rank this result properly in according to user needs. But what we saw from e-commerce search, relevancy formulas will never work for e-commerce search. And I have some arguments for this position, and we can come back to it if you wish. Nevertheless, Lucene accepts this problem and address it by providing mean should match functionality, which is not like, I might be wrong, but classic information retrieval says nothing about such sort of constraints. So it's something like response for practical challenges. No. You can say that all terms are optional, but you require the match at least 2 terms or more terms, and you do not accept matches with one word. That's what mean should match does, and it's functionality of standard Boolean query in Lucene. So it works for ages there, and you actually know everything to implement this constraint by your own. So do you have an idea how mean should match can be implemented in Lucene queries? Given that algorithms which we saw before, do you have an idea how to do that? How to make disjunction queries stricter? Right. How to cut off weaker matches from disjunction query? It was done something like this. Snippet from disjunction sum scorer. Look what it does. It starts loop, right? And in this loop, it picks up top scorer from top of the scorer heaps, move it to the next document, and then adjust the heap. And while heap is adjusted, it calculates number of scorers which are positioned on the same document and evaluate the mean should match criteria. And if this predicate is resolved, it breaks the loop. Right? What it reminds to you? Have you seen this algorithm before? We saw this algorithm in here, right? It's absolutely like this, right? We just loop through the disjunction result and apply matching predicate. So it means that I told you quite smart thing. You can trust it and rely on it because it's repeat the code which is written in Lucene, right? So I gave you really nice advice about creating custom queries. Okay, it might be. So But let's try to filter this query. And before we filter this query, we need to remind what is filtering in Lucene. So it's a standard functionality, and you can tell me why filtering functionality is important for practical application. You should. So why filtering is important for us, for eCommerce sites? Because every site now provides faceted navigation, right? With this left navigation bar. So Lucene also address this challenge and provide filtering facility in its core. So, and the filtering is something like searching without score, right? And if query is a factory for creating scorer, that filter is some sort of factory for creating doc set ID iterator. It's something like parallel abstractions, and there are few ideas to collapse them into single one, right? Just get rid of one of these abstractions. Okay, and here's how filtering is implemented in Lucene 4. Index searcher has additional method which accepts filter in addition to query and collector, and you can see what it does internally. Just wrap query and filter by filtered query, and filtered query is just specialized form of conjunction. It just purports to high performance or more efficient intersection between query and in the given filter. And more than that, it provides few strategies for do it in the best way. So what you can get from these slides, that if you have some performance issues with filtering, right, you can wrap query and filter by your own and specify the necessary strategy, or even implement your own strategy complies with your particular problem. Okay, and let's try to filter min-should-match query. Let's start from this long disjunction query, right? What do you think? Whether it's fast or slow? What's the length of result from this query? It's from long disjunction. It's obvious? What do you think? Just disjunction. Long disjunction. Whether it's expensive or it's cheap and fast? Come on. Okay, thank you. It should be expensive, right? It should provide a really long list of results, right? And so it's just reasonable consequence from Lucene consideration, and it fits to our expectation quite well. And what if we filter this huge query by highly selective filter? And this filter is highly selective because it refers to ID fields. So what do you think about it? Whether it's fast or slow? Faster, because despite this query is expensive, right, that highly selective filter advanced it quite fast through few results, right, and this is it's really fast query that produces really short result. And if we add min-should-match constraint, it became much worse, right? It stopped to perform, right? It runs slow again. What's happened? It looks something like this. Here's the iterator produced by highly selective filter, and here's the scorer produced by that huge query with min-should-match. And when iterator advances that score to the particular document, let's say 100, right, it starts to loop, right, in the code we saw before, right? It starts to loop by disjunction query result and evaluate the min-should-match predicate. What it does. And after it loops for a few thousands of documents, it finds the matching document and return it as result of advance because of contract of method, right? It's what it should to do. But from filter point of view, there's no sense in doing it because that filter can match only single document, right? And there's no way to hijack control from or break this loop earlier. Right? There's not just API. And it was our idea about this problem. So we blame the API, the interface of scores, and consider it as API design problem. But I submitted this question to the Stammsjump a year ago in Zinsheim, and besides I won the prize, we had a valuable discussion with Stefan Paul, who actually present right now at 2 stages above, and he's really smart and competent engineer, and he brought our attention to how this query is executed. Right? It looks so. For example, we have min should match equal 3, right? And this query need to scan all results from disjunction query. So we check this predicate for document number 5, then for document number 7, then for document number 10. But you can see that there is no sense in doing this, because whatever you meet in first 2 posting lists, it doesn't help you to resolve min should match constraint, right? It's reasonable. So instead of this, it should somehow to figure out how to do that, where to advance these 2 scores and call advance on them and move them beyond the document where the 3rd score is positioned right now, that gives some chance to resolve min should match predicate, right? After this discussion, I raised this issue. Stefan provided his implementation of this algorithm, and Robert and Michael McCandles checked the performance and had a lot of valuable suggestions for that algorithm. This algorithm was released in Lucene 4.3, and you can see the performance benchmark, which was attached to this Jira. And the performance gain is a column in 4th column, and you can see that for certain tests it gets 4 digits % gain. It's really amazing optimization for these type of queries. So coming back to our queries, to our case with query customization, what we can take away from this optimization, which was applied to standard min should match query. So it means that if we implement our custom queries just like match verification routine, which will filter out results from base disjunction, right, we might face some performance problems, right? And ideally, what we need to do in that match verification logic, we need to figure out which scores to advance and where, right, to make it run faster. And if we do so, that Lucene will comply to our expectation and to their design consideration. Otherwise, we might be in trouble. So now you know all caveats about performance. Last thing for this talk is one more example of query customization, which is not about search, but about gathering additional information from the search result. So let's look into this example. Here's our documents. And let's we have some query which runs on these documents, and this query matches some of these documents. And it matches them by certain terms. It looks something like this. Let's remove mismatched documents and terms, right? And what we can see here, that we match documents by few fixed patterns, right? And these patterns which we matched the document might be really interesting for us. But now, in default functionality, we lose this information completely. But we can implement custom query, which will accumulate, just aggregate the information about matching patterns, right? It gives us a better understanding of our search result that can allow us to raise few hypotheses about user motivation. So it can look something like this. So we just collapse the same matching patterns like this by using bag data structures, this counting math, right? As a result, we have facet counted on matching patterns, right? We should not provide this information to the user because it's too complex for them, but it's really valuable, for example, for our business rule engine or for our search analytics. So we can provide some sort of redirects and apply some filters automatically. We can just try to recognize user needs, right, by this simple approach. And you know everything to implement this on your own. You need to create MatchSpotting Scorer, which analyzes position of children's scorers, watch them, and recognize matching patterns. Just pick up terms from the subordinate clauses query, which produced scorers which are positioned on the same document as parent scorer, right? And you can return these patterns from separate method and create collector, which will request this pattern alongside with score and document number, right? And just put this pattern into the bag, right? And now you can use it information whenever you want. You can send it to search analytics, to the rule engine, and so on. That you can do on your own. That's just simple hack which can bring additional value for your business. That's all for me. We have plenty of time left. I'm open for your question. That's all for me. How do you find it? Is it worse.end? Okay, thank you. Is there questions or concerns? Maybe you caught me on some misguided information. Maybe I was wrong. Or here is a shortcut to access the slides. Any concerns? Let me repeat the question. The question is how to resolve an ambiguity in user input. There is no silver bullet for sure. It's just the certain undeterminism in it. So it's undefined. We find so the best thing which we can do is just consider this information as a clue about what user might need. So, or it just record how we answered to this request. So if we can conclude it, if in vast majority of results the pink rose is a brand, so we might guess because we have documents which is relevant to user needs because he already chooses our site, right? He might know this brand and we might conclude that he searched for a particular brand and applied as a major hypothesis about their motivation. But the question is open. We have no general solution. We cannot read minds of our users. We try to do that, but there's no cheap answer about it. Okay, there was two assumptions or two ideas. The first idea was about using case from the user input, and from our experience, we watched the query logs quite intensively. Users rarely uses shift button. You know, you might want it, but they never do that. And the second suggestion was that we need to think like bilateral, right? We can always consider the binary hypothesis about user needs. Sure, like we can redirect users. So if we have some idea or guess what brand she searches for, we can redirect her to this landing page of this brand, but provide some link to the other search result, or you might also mean this, but we cannot have this silver bullet for this. Yes, please. Performance problems, if you implement... So you're asking about the coverage match query. Yeah. Right. And the question is where we met the performance problems, is it? And the answer is, let me think about it. I don't think that we've got a performance problem in particular with it. No. There was no performance problem, because if you implement it accurately, right? If you know where to advance certain score, there is no problem. No. The question was, is it still a problem about the performance gain with term time? Is it worth to care about term time performance gain if we have early termination? I'm not really ready to answer. So it can be just two steps in same direction, and they might help to each other. Early termination. But early termination is triggered by this certain length of result, right? But if you do early termination, you need to find only few results. So you might try it actually. If you have early termination, you don't need to worry about basic query performance. So you might be very fine enough even with slow queries, because you can terminate them earlier. So it might be a great hint of addressing performance problem. Early termination is good stuff, definitely. Thanks. Any other questions? Okay, see you later. You can ask me whenever you want, or contact me offline. You are welcome. Thank you very much for attending.